Hi, so this will be a review for test 3, and again, usually I'll just go through some of the questions on the practice test. And so I'll start with number 1a. We want to graph the function y is equal to x minus sine x on the closed interval from 0 to 2 pi, using all the techniques of calculus, right? So find the relative maximum minimum points, inflection points, right? Increasing, decreasing, concave up, concave down, all that stuff, right? So first, we'll take the first derivative, right? Or just y prime if you prefer. And so that's just going to be 1 minus cosine of x. So to find the critical numbers, we'll set it equal to 0. And we get that cosine of x is equal to 1. And where does that happen? On the unit circle, it happens on the right side, right? So when x is 0, or 2 pi, or 4 pi, so basically every multiple of 2 pi. And so in this situation, we're only going from 0 to 2 pi. There's only two solutions, basically 0 and 2 pi. And those are the endpoints, right? So effectively, everywhere between 0 and 2 pi, just pick your favorite number, right, on that interval. How about pi right in the middle? When you plug in pi, you just get 1 minus cosine of pi is -1, so you get 2, which is positive. So that means the derivative will be positive everywhere, at least between 0 and 2 pi, between the two endpoints, right? So that tells me that the function is always increasing, at least increasing on the, we'll say, the open interval from 0 to 2 pi. Okay, right. So no critical numbers between 0 and 2 pi. And so no maximum or minimums, right? Well, specifically, no relative maximum or minimums. Okay, so I think that's it for the first derivative. The second derivative is just going to be sine of x. So where is that 0? All the multiples of pi. So for our situation, that means 0, pi, and 2 pi. So if this was the first derivative, for the second derivative, again, we're not going to worry about the endpoints, but we do have to worry about pi. And if you plug in pi over 2, you get a positive. And if you plug in 3 pi over 2, you get a negative, right? So that means the graph is concave up, concave up from 0 to pi, and concave down from pi to 2 pi. And since it changes concavity, we have an inflection point at pi. Oh, so the y-coordinate will be pi minus 0, which is also pi. So pi, pi, x is pi, y is pi. Right? And I think that's it. So nothing else funny going on. Now let's look at the endpoints, right? Obviously, if we plug in 0 into the function, we just get 0. If we plug in 2 pi, we just get 2 pi. And we already noted that if we plug in pi, we get pi. So as far as the graph goes, again, forgive the slight sloppiness here. This will be pi. This will be 2 pi. This will be pi. And this will be 2 pi. And I think that's all we need. So let's just plot the points. 0, 0, pi, pi, and 2 pi, 2 pi. So be careful. It's obviously not a straight line. We know the graph is going to be increasing, but it's going to be concave up from 0 to pi. So concave up basically means this, right? And then from pi to 2 pi, it'll be concave down. So that's it, right? That's the basic graph, at least from 0 to 2 pi, right? And it would keep going, of course, right? So the graph effectively just does this, right? So it's like a weird step function, but it's, you know, more wavy, continuous, rather than, you know, like that. So yeah, that would keep going, but at least from 0 to 2 pi, that's just one step of it. Okay, so I don't think there's much more to say about part A. Part B, I think you can handle that. It's just a polynomial. So let's go on to part C. Okay, so we're going to graph y is equal to t times the square root of 4 minus t. So realize that, yeah, we're not talking about x anymore. We have the t-axis over here, and then the y-axis is the vertical axis. So, right, so this will be y as a function of t instead of x. But other than that, oh, well, again, first thing we're going to do is take the derivative, so maybe I'll rewrite it this way to take the derivative, right? So first we want to find the critical numbers. Actually, even before we do that, what's the domain? What are we allowed to plug in for t here? So notice that whenever you're taking the square root, what's under the square root had better be non-negative, which means t has to be less than or equal to 4. And now I realize my mistake. This is going to keep going here. Yeah, so t can be negative, right? But it can't be bigger than 4. So let's do 1, 2, 3, 4. And we can do -1, -2, and so on, right? So those will be my t values. But yes, so the domain, we're only going from -infinity up to 4. We can plug in 4, of course. When you plug in 4, you get 0. Obviously, when you plug in 0, you also get 0. So we have these 2 points, right? 4, 0, and 0, 0. I don't want to make them that big. Okay. All right, so domain, very important, right? And now the critical numbers. So take the derivative. So this is a product, right? We need the product rule. First times the derivative of the second. And then the derivative of 4 minus t is -1, so don't forget the chain rule as well. Plus second times the derivative of the first. So that's just 4 minus t to the 1/2 times the derivative of t, which is 1. So this, again, maybe we should rewrite this in a better format here. This is just going to be t over 2 times the square root of 4 minus t. And then, with a minus sign, right? Times -1, right? And then plus the square root of 4 minus t, right? Which we can write over 1. And you might want to write this with a common denominator here. So the common denominator is 2 times the square root of 4 minus t. Again, you don't have to, but I think it might be helpful in this case. So we have -t plus 2 times, and then the square root times the square root. You just get 4 minus t. So that's going to be 8 minus 2t minus t, so 8 minus 3t. All over 2 times the square root of 4 minus t. Okay, so that's the derivative. And remember, in order to find any maximum or minimum points, we need to find the critical numbers. So where does this equal 0? Right? And to that end, we didn't have to do this simplifying. We could have set this equal to 0 way up here. The problem with that is, you know, it's going to take a little bit of algebra. And so we did all the hard work here. Now, where does this equal 0? When 8 minus 3t equals 0, which means t is going to be 8 over 3, right? Or 2 2/3. So Right, so that's going to be, right about here. But what's the, yeah, if you missed that, it's, yeah, right about here somewhere. That's 8 over 3, right? Yeah, so what's the y-coordinate? So let's plug this into the original function. So that's going to be 8 over 3 times the square root of 4 minus 8 over 3. So we get 8 over 3, and then this is 12 minus 8 is 4 over 3. So square root of 4 over square root of 3. So that's just 2. So 16 over 3 square root of 3. And we can simplify that even further. We get 16 square root of 3 over 9. Let's write that a little bit better. 16 times the square root of 3 over 9. And so that's about 3.079. So it's about 3.1, right? So 3.08. So for the graph here, we're going to go up 1, 2, 3, and then this would be 4. So it's just a hair above 3 here. So if this is 8 over 3, we go up to just over 3 here. In fact, that might be a bit of an exaggeration. So let's try that again. Go up. Okay. So that should be our, well, it looks like it's a relative maximum. Again, we don't know that. All we know is that we have a critical number at 8 over 3. And so if you use the first derivative test, you'll see, right, that we're going from a positive to a negative. Right, so we do indeed have a relative maximum at 8 over 3. Okay. In fact, let's label this point here. 8 over 3 is the x-coordinate, and 16 square root of 3 over 9 is the y-coordinate. And again, that's approximately 3, a little bit bigger than 3. Okay, so I think that's the only critical number, which means that's the only relative maximum we have. What about the second derivative and the concavity? Well, okay, so we took the first derivative. Let's just rewrite it. So this is 8 minus, oh, well, okay. Let's write it as a product, right? So 1/2 times 8 minus 3t times 4 minus t to the negative 1/2. And maybe we'll just use the product rule here. We could use the quotient rule almost as easily. Okay, so the 1/2 is just a constant. And then first times the derivative of the second. And by the chain rule, we're going to get another negative, so that'll make that positive. 4 minus t to the negative 3/2, right? So, and times the first, which is 8 minus 3t, plus second times the derivative of the first. The derivative of the first is just negative 3. So let's see, putting this all together, we're going to get 8 minus 3t again, but this time divided by 2 times 2, which is 4. And then we have 4 minus t to the 3 over 2. And then we're going to have, let's see, a negative 3 over 2. Right, so plus negative 3 over 2, and then 4 minus t to the 1/2. So to get a common denominator again, let's multiply by 4 minus t. Right. Oh, and another 2 here. Yep. To get 4, right? Okay, so now we should have our common denominator. It's going to be 4 times, do it again, 4 minus t to the 3/2. And on top, we just get 8 minus 3t, and then plus a negative 6 times another 4 minus t. So multiplying all that out, the numerator becomes, let's see, 6t minus 3t is 3 times t, and then 8 minus 24 is negative 16. Right? So I didn't need a fraction that big. So to find the possible inflection points, right, we set this equal to 0 again, and now we get t is equal to 16 divided by 3, which is 5 1/3. So that's a possible inflection point, right? Remember, we still have to check for the second derivative whether the sign of the second derivative actually changes. So let's see, 16 over 3, where's that? Oh, so that's way over here somewhere, right? Notice it's bigger than 4. It's not even in the domain. So, yep, 16 over 3 is not in the domain, so we ignore it. Okay? So that means there's no inflection points. The second derivative does not change sign. If it doesn't change sign, then what is it going to be? So plug in any number on the domain into the second derivative. 0 works. 0 is less than 4. So that's just going to be negative 16 divided by 4 times the square root of, what is it? 4 cubed. So that's going to be square root of 64, which is 8. So I think we just get negative 1/2, which is clearly negative. So that tells me that the second derivative will be negative everywhere. So it's going to be concave down. Graph is concave down everywhere. Concave down. Right. And we already know it's going to be increasing to the left of 8 over 3 and decreasing to the right of 8 over 3. So when you connect the dots, and there's only the 3 here, it's going to look something like this. Oh, that's a little sloppy, but you get the idea. And then it does keep going downward like this. So it is concave down everywhere. Right? I'll fix that just slightly. It's concave down everywhere. It is increasing and then decreasing, and then this is your relative maximum. And that's it, right? There's no arrow here, right? Remember, the graph does not keep going this way. It stops at 4. So this is the right-hand endpoint. Yeah, so 4, 0 is as far as it goes to the right, but it does keep going to the left forever. And that's it. So pretty standard. Again, just the tricky thing with the square root is turn it into an exponent and then use the product and quotient rules wherever necessary. Should we do one more graph? I think E, we did one like E before, so how about D? Right, so we'll do 1D. Right, so which is just the function g of x equals x over x to the 4th plus 1. So domain. So I hope you can tell it's all real numbers, right? The denominator will never be 0. In fact, the denominator will be greater than or equal to 1, because x to the 4th has to be non-negative, so at least 0. And when you add 1, you just get something bigger than 1. Okay, so if you try to solve this equation, you'll get no real solution. Okay, so domain is all real numbers. All right, so critical numbers, we need the derivative. And in this case, I'll just use the quotient rule directly. So denominator times the derivative of the numerator minus numerator times the derivative of the denominator, all over the denominator squared. And we can simplify that a bit. We get 4x to the fourth, or sorry, x to the fourth minus 4x to the fourth, so negative 3x to the fourth plus 1. So where is that 0? Oh, I'm running out of space. Okay, so 3x to the fourth equals 1. X to the fourth is going to be 1/3. And so this should have two solutions, one positive, one negative. This is the fourth root of 1/3, or 1 over the fourth root of 3. So approximate that. Right, and according to my calculator, you get about 3/4. It's 0.759, so we'll say 0.76, plus or minus, right? So two critical numbers, one positive, one negative. So what happens at 0? We know we get a positive. If we plug in something bigger, then this negative dominates, so we get a negative here and a negative here. So we have a minimum at the negative 0.76 and a maximum at positive 0.76. So relative minimum. Again, forgive me for using the approximate here. And a relative maximum, positive 0.76, right? All right, concavity. So now we need the second derivative. Okay, I'll try to squeeze it in here, but I'm going to have to figure out where I'm going to put the graph. So second derivative, we'll just take the derivative of this using the quotient rule. So low d high minus high d low. So denominator times the derivative of the numerator minus numerator times the derivative of the denominator, chain rule, all over the denominator squared. And when you square square, you get to the fourth power. So x to the fourth plus 1, all to the fourth. And, you know, we should simplify this a little bit. Notice that we do have a common factor of x to the fourth plus 1 everywhere in the numerator. And what do we get then? We get negative 12x to the 7th minus 12x cubed minus, so I can't do this in my head, minus 8x cubed times 1 minus 3x to the 4th. So I'll work that out on the next step. The denominator is the same. And while we're at it, we can cancel 1 with the numerator. So that means the denominator will just be x to the 4th plus 1 to the 3rd power cubed. And what do we get? We get, let's see, 24x to the 7 minus 12x to the 7 minus 12x cubed, and then we're going to get a negative 8x cubed. So I think that's going to be 12x to the 7 minus 20x to the 3. So where's that possibly 0? Well, we know one of them is going to be at 0 here. So for the numerator, we can factor out a 4x cubed. And that's going to leave us with 3x to the 4th minus 5. So clearly, we might have an inflection point at 0. And then x to the 4th will be 5 over 3. So we also have plus or minus the 4th root of 5 over 3. And again, I'll just run to the calculator and see what we get. It's about 1.14. So just a hair above 1. All right, and now do the signs actually change at these 3 points here? So here's positive 1.140 and negative 1.14. So let's see, this is clearly going to be positive to the right. And then, let's see, so if you plug in 1, this will be negative here. Right, so it's a positive times a negative, so that's negative. And if you plug in negative 1, same thing, this will be negative, and then this will be positive, right? So we only have inflection points at these values here. 0 is not an inflection point because the concavity does not change at 0. All right. That should do it. Now just for the graph. So what do we have? We have 0, 0. And then at about 3/4, so let's draw a slight scale here. Here's 1, here's 2, here's negative 1, negative 2, and so on. Okay, well, so I never plugged in 0.76 into the original function. But if you did, I think you get about 0.57, so just barely 1/2 here. So let's write that down here. So G of 0.76, sorry, is about 0.57. That's where I got confused. Okay, so if this is 1 and this is negative 1, we don't even go up halfway here. So, well, we go a little more than halfway, right? And I think if you plug in the negative, yeah, you just get the negative version of that. So right about here. Right. So this gives you a maximum at the positive. And a minimum at the negative. I think it looks like that, right? Yeah, so we have an inflection point right about here, right? So here it's, maybe I didn't draw it quite right. Here it's still concave down, and then it changes to concave up. And here it's concave up, and then right about, let me mark these points clearly. I'll do them in purple. These are the inflection points, right? So this is inflection, and right around here as well. So 2 inflection points. 0 is not an inflection point. Oh, well, isn't it? It's concave up and then concave down. Oh, it is an inflection point. See, I think I got this backwards then. Yeah. So this should not be positive here. This should be negative. So they alternate, right? Negative, positive, negative, positive. Let's see, what happens if you plug in negative 1? Oh, that's right. This is negative, and then x cubed is also negative. So it's a negative times a negative. Okay, so my sign chart here was wrong. Now it's correct. So, yeah, so I was wrong. 0, 0 is definitely an inflection point as well. Yeah. So 3 inflection points. 0, 0, and then right about 1.1 and negative 1.1. Again, slightly exaggerated, but that's the idea. So that's, again, a rough sketch of the graph. And I think you can handle the others. Obviously, tangent for part F, you've hopefully seen that graph before. But now you're going to get a little more detailed when you look at the second derivative, the concavity of tangent. But so that's graphing. I hope that helps. Right, so number 2 is also a graphing problem, and a slightly more interesting one because we never give you what f of x is, right? We don't give you the original function. as in terms of an equation here, right? So we don't know what f of x is, but somehow using this information, we want you to come up with some sort of a reasonable sketch to the graph. So we have 0, 1, 2, and so on, right? So I might change my scale a little bit here. This is going to be 1, this is going to be 2, so -1, -2. So what do we know? So this first condition here, f of 0 equals -2, just tells us that x is 0, y is -2. So that gives us a point on the graph. In fact, that's the y-intercept, 0, -2. And then f of 2 equals 2, so when x is 2, y is 2, so that's a second point on the graph. But that's it. In terms of these points here, we have 2, 2, and 0, -2. And that's it. The derivative at 0 is 0, and the derivative at 2 is 0. So that tells us that we have a horizontal tangent line at 2, 2, and 0, -2. Okay. The first derivative is negative when x is negative. So when x is negative, we know it's going to be decreasing. So that's decreasing, right? I mean, from left to right, it's decreasing. Obviously, if you're reading backwards, right to left, it looks like it's going up. But remember, we're always going from the negative to the positive. So it's decreasing. And then it's going to be greater than or equal to 0 for x positive. Now we know where it equals 0 is at x equals 2. Right? And then it's going to be concave down from 1 to 2, but concave up everywhere else. So we don't know exactly. So this is going to be tough here. So it's going to be concave up, and then at 1 it changes to concave down. Right? And since it's still concave down, oh no, I'm sorry, it changes to concave up. Right, the first derivative is positive, so it's got to be increasing. It's got to be doing that. Okay, so again, a very rough sketch here, but I think that's the idea. Okay, so I think, yeah, concave up everywhere except, where's it concave down? Just from 1 to 2. So this is where it's concave down. Still increasing, but concave down. Right? Okay, so that's it for number 2. Number 3, I think I'll skip because we've done several like that already. And in fact, number 4 is also fairly routine, but let's do it. Find the relative maximum and minimum points of this polynomial function. And in case it's not clear, let me just copy down the function. This is going to be -2x to the 5th plus 5x to the 4th, plus 10x to the 3, plus 1. And, right, they don't give us the domain, but it's a polynomial, so there's no issue. The domain is all real numbers. So where do you get maximum and minimum points? Only at critical numbers. So we have to find the critical numbers. How do we do that? Take the derivative. And set it equal to 0, but also where the derivative does not exist. Well, since it's a polynomial, the derivative will exist everywhere. So the only critical numbers here come from where the derivative equals 0. Again, that's not always the case, but for most functions, it usually is, right? Let's see, what can we do? We can factor out, how about a -10 x squared, and that leaves us with x squared minus 2x minus 3. So we have -10 times x squared times x plus 1 times x minus 3. Oh, I should write it the other way, although it doesn't matter. So x minus 3 times x plus 1. Yeah, so we get three critical numbers, 0, 3, and negative 1, obviously not in that order. So here's negative 1, 0, and then 3. Right, so three critical numbers, and now just to figure out whether we have a maximum or minimum, we'll use the first derivative test, or you can use the second derivative test, but I'll just use the first. Right, so when you plug in, let's say x equals 4 into the first derivative, I'll do that down here. What do we get? Well, we get negative 10 times 4 squared is 16, times 4 minus 3 is 1, times 4 plus 1 is 5. So we get a negative number, right? It's a negative times a positive. I think it's negative 800, but negative 800. Again, we don't care what number it is, we just know that it's negative, right? Okay. So notice that the exponents at 3 and negative 1 are odd numbers, so that's where they alternate. But at 0, we have an even exponent, so that's where it stays the same. Okay. So you can get the sign chart fairly quickly by just plugging in one number. In this case, I plugged in 4 here, and then using the multiplicities, the exponents of the corresponding factors. Right. And if the exponents are odd, the signs alternate. If the exponents are even, the signs stay the same. Okay, so based on that, we know we have a minimum at negative 1 and a maximum at 3, and neither at 0. Right? 0 is not a relative maximum nor a minimum. So 0 is neither. 3 gives you a maximum, and negative 1 gives you a minimum. And they do ask for the points, right? Maximum, minimum points, so we also need the y values. So that's just plugging in the 0 in the original function. You get y equals 1. If you plug in 3 into the original function, that I cannot do in my head, so let me work it out on a calculator. So when x is 3, I get 190, but not sure I did that right. I think it's 190. For negative 1, let's see, what do we get? We just get positive 2 plus 5 is 7. 7 minus 10 is negative 3. Negative 3 plus 1 is negative 2. So, so we have a maximum, well, relative maximum, right, at 3, 190, and a relative minimum at negative 1, negative 2, and then neither at 0, 1. And that should be it for number 4. Number 5, we're given the second derivative, which is x times x minus 1 squared times x plus 4 cubed times 2x minus 5. Okay, so be careful. This is not the original function. This is the second derivative, right? We don't know what the original function is. In fact, we don't even know what the first derivative is. All we know is the second derivative. All right, but look at the question, right? We want to find the open intervals on which the graph is concave up, concave down, and then the x-coordinates where we have an inflection point. Okay, so this actually is pretty standard, right? Notice that this is already in factored form. The last thing you want to do is try to, expand this out and multiply it out. I mean, if you do, you're going to get, let's see, 1, 3, 6, 7, 2x to the 7th plus a bunch of other stuff, which we don't care about, right? So no reason to multiply it out because the whole point is to set it equal to 0. And that will tell us, right? Remember, this is the second derivative, not the first derivative. We're not finding the critical numbers here. This is the second derivative. What we're finding are possible inflection points. So what do we get? We get x equals 0, x equals 1, x equals -4, and x equals 2.5, or 5/2. So these are not necessarily critical numbers, although they could be. We don't know what the first derivative is, right? So we don't know whether these are critical numbers as well. But these are possible inflection points. Right. And I say possible because we don't know if the sign of the second derivative changes. We don't know if it changes concavity. So let's make a sign chart for the second derivative, right? So -4 is the smallest value, then we have 0, then 1, and then 5/2 is 2.5, so that's the last one. So when you make your sign charts, let's see, if x is bigger than 5/2, this is positive, this is positive, this is positive, everything's positive, right? So I think we can say that this is definitely a positive sign. The 5/2 has an exponent of 1, which is odd, so that means the sign alternates. What happens at x equals 1? At x equals 1, we have an even exponent, so the sign stays the same. At 0, we have an odd exponent, right? X to the 1. 1 is odd, so that alternates. And then at -4, we have the exponent is 3, but 3 is odd, so that also alternates. Okay, so again, I want to make this very clear. We have to plug in one of these numbers, and I plugged in, let's say, 3 here into the second derivative. And, well, I didn't calculate it, but it's 3 times 2 squared is 4, times 7 cubed, which is, what, 343, times 1. But whatever number this is, we know it's greater than 0. We know it's positive. So that's where that sign came from. All these other signs just came from the exponents, the multiplicities, right? Okay. Yeah, so again, feel free to do that, but do show what number you did plug in here, right? Because, you know, if you either plug it in wrong, or let's say you get that it's negative instead of positive, then all the others will be wrong, right? You'll basically just flip all the signs and you'll get the wrong answer for everything. So be careful of that. When you do plug it in, make sure that you have the correct sign for that one particular value, in this case 3. All right, so to answer part A, where is it concave up? Wherever the second derivative is positive. So that's from -4 to 0, and then again from 5/2 to infinity. Right. Where is it concave down? Down. It's very sloppy. Concave down, that's better. Wherever you see a negative sign. So from -infinity to -4, and then from 0 to 5/2. Now, let's make sure we understand here. What happens at x equals 1? The second derivative is technically 0. However, when you draw the graph, it's still going to be concave down everywhere. So you can skip through x equals 1. On the other hand, if you did 0 to 1, and then from 1 to 5/2, that's okay too. In fact, I think you're playing it safe. If you do it that way, that's probably better in general. But in this case, we can say it's actually concave down all the way from 0 to 5/2, simply because at x equals 1, the graph is still concave down, even though the second derivative happens to be 0 there, right? It's 0 at all 4 of these numbers. Okay, so that's part A. Part B. Part C, where do you have an inflection point? Well, everywhere the sign alternates. So you have inflection points. Oh, I'll spell it out. Inflection points at x equals -4, x equals 0, but not x equals 1, right? X equals 1 is not an inflection point because the sign does not alternate. The sign stays the same. So at 5/2 is the other one. So only 3 inflection points, even though we got 4 solutions to this original equation up here. There were 4 possible inflection points, and then 3 actual inflection points. Okay, right? Remember, x equals 1 here was not an inflection point because the sign did not alternate. So you have to be aware of that. Right, and that's it, right? We don't have to graph it or anything. We just wanted this information. So effectively, these are the answers here. Okay, so while number 6 is an optimization problem, I think it's a fairly standard one, and it's pretty routine. After all, we give you the function that you have to minimize, and then just show that it's a minimum, right? So given the function, I think you know how to do it, right? It's find the critical numbers, take the first derivative, set it equal to 0, and solve that equation. That gives you your critical number. Then you just have to make sure it is a minimum and not a maximum. So number 6, pretty doable. Number 7, a little bit harder, right? So we have a closed cylinder. So maybe I should draw a cylinder here. And so we're constructing the cylinder so that the cost per unit area of the top and bottom is 3 times the cost per unit area of the sides. So we have the top, this is the top up here, we have the bottom of the cylinder, and then we have the side, which is this part here. Right, and it says that the cost for the top and bottom is 3 times the cost of the side. Right, why would that be? Well, maybe the top and bottom has to be reinforced, right? If this cylinder is to contain, like, let's say liquid, then we need the bottom to be, strong enough to contain that liquid. Right, so the top and bottom cost 3 times as much. So top and bottom have 3 times the cost compared to the side. Okay, so find the radius and the height of the cylinder of a volume that has to be 750 cubic centimeters. So this is also given. Volume, which I'll call V, has to be 750 times pi cubic centimeters. So this is given. And we want to minimize the total cost. To build the cylinder. Make sense? Right, so we know the volume. How do we calculate the cost? Well, right, there's 3 parts to this. There's the top, the bottom, and the sides, right? So let's start with the side. The cost of the side, right? Well, if you unfold this, you just get a rectangle, right? Where this is the side, and then the top and bottom are just these straight lines here, right? So the side, then, if we unfold this, it's just the area of the rectangle, right? So the area, right, the top and bottom is just the circumference of the circle in terms of the radius, so I'll call that R, I'll call this H for height. So the height is the same, but then the top and bottom, this is going to be 2 pi r, the circumference of the circle, right? So 2 pi r for the length, and then the height will be h. Okay, so what's the cost going to be? Well, notice they don't tell us what the cost is. So why don't we just assume that it's $1, per square centimeter? There's no harm in that, right? So $1 times the area is just going to be 2 pi RH, right, times $1 per square centimeter. And since this is the area, this is in square centimeters, right? We get this in dollars here. Right? Okay, what about the cost of the top and bottom? Well, the top is just a disk, right, of radius r. And so the area of that disk is just pi r squared. And how much does it cost? Well, 3 times as much, right? So $3 per square centimeter. Right? Right? But the bottom is exactly the same. Right? The area, it's still a disk, right? It's the same disk, same radius, and the cost is still $3, right? So when you add all these up, you get the total cost is going to be 2 pi RH plus 3 is 6 times pi r squared. Make sense? So this is a function, but notice it depends on both the radius and the height. So remember, our goal is to minimize the cost. So take the derivative and set it equal to 0. Unfortunately, we don't know how to take the derivative because we have two variables, r and h. So what do? We have to eliminate either r or h. And my guess is that because we have only the h here to the first power, let's eliminate h and get the cost in terms of just the radius by itself. Okay, so how do we do that? So we need a secondary, right? So remember, this is our primary equation. This is the thing we want to minimize. And now we need a secondary equation, which relates r and h. What's the relationship between r and h? Well, what's the only other thing we know about the cylinder is the volume, right? And the volume, hopefully you know this, or you can look it up, is pi r squared times h, right? And that volume has to be 750 times pi. So now you know why they multiply this, the volume times pi here, because you can divide both sides by pi, the pi's cancel. And if we want to eliminate h, we can solve for h by dividing by r squared. So h is just 750 divided by r squared. Right? And so this is our secondary equation. And so all we have to do now is plug in, right, h is equal to 750 over r squared. And if we do that, we get 2 pi r times 750 over r squared plus 6 pi r squared. And when you simplify that, we get 1500 pi over r plus 6 pi r squared. And now this is our primary equation as a function of just a single variable r. Okay, so far? Well, now we can do the calculus, right? Well, first of all, what's the domain? The domain is that the radius has to be positive. Obviously, it can't be 0 either. We can't divide by 0. But if the radius were 0, then that wouldn't make sense because we wouldn't have a cylinder to begin with. Okay. There probably is some maximum value of r here, and that'll be clear later. Actually, we can figure that out now. If h is, well, no, wait. If h is 0, then the volume would be 0. So no, there is no, okay, so there is no maximum r, and there's no maximum h either. All right, so the only thing left to do now is to take the derivative, to find the critical numbers. And to do that, usual rules here. So that's the derivative. Where does it equal 0? Well, we can multiply both sides by r squared, but I'm just going to cross multiply here. So 12 pi r is equal to 1500 pi over r squared. So multiply by r squared, and you get 12 pi times r cubed is equal to 1500 times pi. And now just divide by 12 pi. So r cubed is going to be, well, 1500 divided by 12 turns out to be exactly 125. And the pi's cancel, so r cubed is 125. Right. And that cannot work out any better, because when you take the cube root of 125, you get about as nice of a number as you can get, 5, right? So r is 5. 5 what? 5 centimeters, right? 5 centimeters. Right. And that's our only critical number. So that should give you the minimum cost. Again, we'll establish that later. Before we do that, what's the question? Find the radius and the height. Well, we found the radius. Now we just have to find the height. How do you find h? Yep, go back up to the secondary equation up here, right? So if we know r is 5, h is 750 divided by 5 squared. So 750 divided by 25, I think is 30. Right? 75 divided by 25 is 3, times 10 is 30. So 30, again, centimeters, right? 30 centimeters. And that should answer the question. Find the radius and the height that will minimize the cost. Okay, so how do we know this is a minimum cost and not a maximum? We can use the first derivative test, right? And here's the first derivative. So you plug in 4 and 6 maybe into that. I'm actually going to use the second derivative test because it's not that much harder to take the second derivative. So the second derivative is going to be, let's see, 3000 pi over r cubed plus 12 pi. And so when you plug in 5, you just get a positive plus a positive. It's clearly positive. So positive means concave up, which means you have a minimum at r is equal to 5 centimeters. So, yep, we do minimize the cost. We're not maximizing it. Right? So the question was valid. We're minimizing the total cost. Right? And what is the total cost? Well, it's just plugging in c is equal to 5 here and calculating that. Again, that wasn't the question, but we might as well do it anyways, right? So what is the actual minimum cost? So it's going to be 1500 over 5, so 300 times pi. And then, let's see, 5 squared is 25. 25 times 6 is 150 times pi. So I think we get 450 pi in dollars, of course. And what would that be? 450 times pi. Oops, sorry. So $1,413.72. Wow, so that is a fairly expensive cylinder. I don't know, maybe it's made of gold or something, or some very rare metal. Oh, actually, to be fair, we don't know that, right? We don't know that this is in dollars. Remember, I assumed that the side was $1 per square centimeter. It could be 5 cents, right? It could be 2 cents. So, okay, so this is not in dollars here. We really don't know that. Right. So never mind about the dollars. That's, But we know it's 1,413.72 times the cost of the side in dollars. So if it's only 2 cents per square centimeter, then you divide this by 50 and you get a much more reasonable number. Okay, so the units are not in dollars because we never said that it was actually $1 and $3 respectively. That was my just making those numbers up for simplicity's sake. Okay, but yeah, so to answer the question though, find the radius and the height, and that's 5 centimeters and 30 centimeters respectively. Okay, so that's number 7. Okay, so I think we should definitely do number 8 because this is probably one of the more difficult ones. Certainly one of the more tedious and involved ones, but it's also a good problem. So so let's see what we can do here. We have a hallway that's 5 feet wide. Okay, so that's this part of the hallway here is 5 feet wide, meets another hallway at right angles that's 8 feet wide. That's this part here, right? And we're trying to carry a ladder horizontally, and that's the key word, right? Obviously, if we bend it or tilt it, we might be able to fit it around the corner. But if the rule is that you have to carry it horizontally, you see in this picture here, this ladder gets stuck, right? So we're looking from the top of the, we're looking from the top, like from a security camera, right? So we have a ladder. If it's too long, you can bend it, but it's going to get stuck, right? So, so if we have a very short ladder, obviously we can just carry it around, no problem. So clearly there's going to be a ladder that's just too long for it to be carried around the corner where it will get stuck. So what's the longest ladder that does not get stuck? And what we're going to do, if you look at the picture looks like the ladder does get stuck. So this is equivalent to saying find the shortest ladder which does get stuck. Stuck, right? Which means we cannot carry it around the corner. It's just too big, right? And I'm sure you can relate to this. If you're in a very narrow hallway with stairs or something, and you're trying to carry a big thing like a couch, and you can turn it and twist it anyway, but if the hallway is just too narrow, it's just going to get stuck, right? So that's kind of the idea here too. All right, so how do we do this? Well, there's 2 good ways of doing this. One way involves the way that if you read the answer key, right, we draw this triangle here, and notice this is a right triangle. And I label, since we know this is 5 feet here, we don't know how long this is, so I call that x. And we don't know how long this is, so I call that y. And then we just have this big triangle here. I made it too big. There we go. Right, and it is a right triangle. And then this side is 8 plus y, or y plus 8. This side is x plus 5. Oh, I think I got that backwards. It's x plus 8. Yeah, x plus 8. And then y plus 5 is the height. Well, not the height, but the width, right? And so we're looking for the length of the ladder in terms of either x or y. Okay, and again, I'm going to let you do it that way. If you get stuck, of course, you can always get a hint from the answers. I'm going to do it a way I haven't done this in a while. I'm going to do this using trigonometry. So I'm going to use an angle here. I'm going to call this angle theta. And what I would like to get is the length of the ladder in terms of theta. Okay. All right. This is going to involve a little bit of trigonometry. And even if you do it the other way, the algebraic way, there's actually a couple things you have to do here. Notice there's actually three triangles. There's this small triangle here. And then there's this slightly larger triangle here. And if you look at just the ratios of the sides here, if you want the length in terms of x and y, we notice the relationship here between the sides. So these are similar triangles, which means if you take x divided by 5, that's going to be the same as 8 divided by y. In other words, x times y is equal to 8 times 5, which is 40. And so this gives you a relationship between x and y. So this, if you were going to do it, the Pythagorean theorem way, then this is what you would need as well. Right, this would be your secondary equation here. Okay, so again, that's just from using these two triangles here, right? So this is x, this is y again. Okay, well, but we want this in terms of angles. I'm going to do this using trigonometry here, right? So I think the first thing is to essentially relate the red length here, which I'll call L1, and the green length, which is L2. Eventually, we just want the total length, which is L1 plus L2, and these both depend on theta. Okay, so yeah, so remember, this is also theta here. These are similar triangles, so they have the same angle. And so let's see, what do we know? We know that if we take the cosine of theta in the first triangle here, let's see, can I write it down here? For the green triangle, the cosine of theta is adjacent over hypotenuse. The adjacent is 8, and the hypotenuse is L2. Right? So that tells me that L2 is 8 divided by cosine, or better yet, 8 times the secant of theta. Right? And now for the red triangle up here, if we take the sine of theta, we get 5 over L1, which means L1 is just going to be 5 divided by sine, or 5 times cosecant. Cosecant of theta. Okay. And so there's our answer, right? L1 is just 5 times the cosecant of theta, and L2 is just 8 times the secant of theta. So there's the total length of the entire ladder, L1 plus L2, strictly as a function of theta. So we didn't need any secondary equations here. We just got it by adding L1 plus L2. Make sense? Okay, well, if that's our function, L is a function of theta, how do we minimize it or max it? Well, again, depends on how you read the question, right? If you read the question by saying we want the longest ladder, it looks like we're maximizing something. But in the picture, the ladder is stuck. So we actually want to find the shortest ladder. We want to minimize L, right, as a function of theta. Okay, so how do I minimize something? Well, find the critical numbers, right? So take the derivative and set it equal to 0. Okay. Well, the derivative of cosecant is negative cosecant times cotangent, I hope you know that. Plus, and then the derivative of secant is secant times tangent. Again, very handy if you know those. So that's the derivative. Let's just set it equal to 0 and solve for theta. Yeah, so this does not look pretty, right? This does not look like an easy equation to solve here. So what I'm going to do is relate this to the more familiar functions of sine and cosine. Okay, so cosecant, remember, is 1 over sine, and cotangent is cosine over sine. Plus 8 times secant is 1 over cosine, and tangent is sine over cosine. So the equation here reads -5 times cosine over sine squared plus 8 times sine over cosine squared equals 0. Okay, so we could get a common denominator, or we can just cross multiply. And I think I like the cross multiplying a little bit easier here. So this is going to equal, if I add the 5 cosine over sine squared to both sides, cosine in the numerator, sine squared in the denominator. Right, so now just cross multiply. And if you do that, you get what? You get 8 times sine cubed, right? We have sine times sine squared is sine cubed, equals 5 times cosine squared is cosine cubed. So if I divide by, let's see, if I divide by 8 times cosine cubed on both sides, what do I get? I get sine cubed over cosine cubed, which is tangent cubed, is equal to 5 over 8. Okay. And if you did get a common denominator here, eventually you'll get the same equation here. So how do I find theta? Well, okay, so if we take tangents to the third power is equal to 5 over 8, just take the cube root of both sides. So the tangent of theta is the cube root of 5 over 8. And I don't know, let's see, 5 over 8 is 0.625. If I take the cube root of that, I get that this is approximately 0.855. I think that's right. So now, if that's the tangent of the angle, how do you find the angle itself? Take the arctangent or inverse tangent. And again, that's a calculator problem. So on the calculator, let's see, the arctangent of, well, I'll do the cube root of 5 over 8 to be more precise. I get 40.53 degrees. So we'll use degrees instead of radians here, right? So 40.53 degrees. So it's roughly 40.5 degrees. Right. This is our one and only critical number, right? There's only one critical number here. Remember, we set the derivative equal to 0, and when we solve for theta, we got this angle, theta, right? And yeah, if you look in the picture, that looks about right. Theta is about 40 degrees or so. So I think that's about right. Okay, so what was the question, right? Find the length of the longest ladder, or rather the shortest ladder, which gets stuck. So now that we have our angle, we plug it into the original function. And just to remind you, the original function, L of theta, was what? 5 times the cosecant, or better yet, maybe 5 divided by the sine, plus 8 divided by the cosine. Right. So if we plug in 40.53 degrees, well, let's do it exactly. Let's see, we're going to get 5 divided by the sine of 40.53 degrees plus 8 divided by the cosine of 40.53 degrees. Plug all that in your calculator. And I'm getting 18.219, so 18.22. And that's the length, right? That's going to be in feet, 18.2 feet. Okay. So, right, so the length of the shortest ladder that gets stuck, right, so the length of the shortest ladder that gets stuck is about 18.22 feet. Right. Of course, right, the question says find the length of the longest ladder. That clears the hallway, right? That does not get stuck. Right. But it's the same answer. So the reason why it really should be the shortest ladder, we are minimizing something, right? We are minimizing the length of the ladder that does get stuck. Okay, so it's a minimum L, not a maximum. And the way to see that is, the way to see that is to either take the second derivative. So where was the first derivative? The first derivative was right here. And yeah, you got to use the product rule twice. So maybe we'll just use the first derivative test, right? So here's L prime of theta, and our critical number was what? 40.5 degrees roughly. Degrees, not cubed. Sorry. 40.5 degrees. So what number should we plug in here? Well, what's less than 40 degrees? How about 30 degrees, right? So if you plug that into the derivative, I think we get a negative. I forgot exactly what we get. We get a negative, right? Right. And what's bigger than 40.5 degrees? 60 degrees. So if we plug 60 degrees in, we get a positive. So we're going from a negative to positive, which means we get a minimum. So don't get disturbed by the question that says find the longest ladder, right? You're not maximizing something, you're actually minimizing the length. So, right, because in the picture here, the ladder does get stuck. Right. When the ladder doesn't get stuck, then it's a very short ladder, and then it has no trouble clearing the hallway. You just turn around, turn the corner. Okay. So yeah, that was the version using trigonometry. And again, I haven't done it this way in a while. But you can also use similar triangles here and use the Pythagorean theorem and do it a more algebraic way. But you can look up the answer key. It's not completely detailed, but it does go through a few of the steps that you would have to go through to solve it using L in terms of x rather than in terms of theta. So again, by using this as your secondary equation, you can get the length strictly in terms of x, right? But it's going to be a sum of square roots, and so that's not going to be pleasant either. So personally, I kind of like doing it using trigonometry here, but if you want to do it the other way, that's fine too. Either way, you get about the same answer, right? 18.22 feet is the longest ladder that does not get stuck, or the shortest ladder that does get stuck. All right, so that's number 8, and that's probably one of the more difficult ones. So let's do one more that's hopefully not quite as difficult. All right, so one more optimization. And between 9 and 10, I'm going to do 10. Number 9, I think there's an example in the book that's pretty similar to number 9. So I'm going to do number 10. We want to maximize the area of the rectangle inscribed in the region between the x-axis, the y-axis. So it might be helpful to draw the graph here. Here's the y-axis, here's the x-axis. And the graph of y equals 16 minus x to the 4th. So that's just an upside down, well, it's actually not a parabola, right, because it's to the 4th power. But the graph will look something like this. Okay, so this is the graph of y equals 16 minus x to the 4th. Right. So somewhere in here there's going to be a rectangle, right? So it could be very thin, like this one here. Pretend that's a rectangle, right? It could be very short, but a very wide rectangle. But these are not very big rectangles, right? I think the biggest one, the one with the maximum area, is probably somewhere in between, probably something like this. So that's a pretty big rectangle, right? Is it the biggest? Well, that's the question, right? Right, find the largest area, maximize the area of the rectangle. So because it's inscribed, and this is the key here, this point that's on the rectangle and the curve here, right, has an x and a y coordinate. The x is somewhere here. It's somewhere less than 4. In fact, we can say it's between 0 and 4. This is the domain. But the y coordinate is simply given by this equation here, right? Because it's on the graph of, it's on the curve. It's on the green curve here, right? So really, if x, right, we don't know what x is, but y in terms of x is just 16 minus x to the 4th, right? In other words, this equation here, right, this is your secondary equation. It's given in the problem. What is the primary equation? Well, what are we trying to do? We're trying to maximize the area, right? So the primary equation should be area. Area of what? Area of this rectangle. This red rectangle here. So now I'm making it yellow, but it's, right. So the area, of course, is just length times width, right? X times y. Right? So, yeah, this is x, the height is y. But remember, we know what y is. It's 16 minus x to the 4th. So, right, your primary equation depends on both x and y. But by plugging in the secondary equation, we get it strictly in terms of x. So now we have a function of x. Area as a function of x is x times 16 minus x to the 4th. Right, so to find the critical numbers, we take the derivative, set it equal to 0. Again, make sure you note the domain. X is between 0 and 4. We could say equals, but then there's no rectangle, right? Then the area would be 0. So yeah, how do we find the derivative? The usual way here. I'll write it both ways. Well, actually, product rule, right? X times 16 minus x to the 4th. So if you want to avoid the product rule, let's maybe just multiply this out. We get 16x minus x to the 5th. Now when we take the derivative, we get 16 minus 5x to the 4. Right? So the only critical numbers come from where this equals 0. So when you solve for x, you get x to the 4th is 16 divided by 5, which means x is going to be plus or minus the 4th root of 16 over 5. And the 4th root of 16 is 2, so 2 divided by, the 4th root of 5. Okay. So we get two critical numbers, one negative, one positive. But guess what, right? The domain, x has to be positive, right? We're not going over here where x is negative. That's not part of the, it's not part of the graph. So there's only one critical number. It's positive 2 over the 4th root of 5. And so what is that approximately? So take the square root of 5, take the square root of again, flip it over, and multiply by 2. And I get that this is approximately 1.3375, which they didn't say how far we want to round, so maybe 1.34 is good enough, right? 1.34 units. So that's our critical number. What's y going to be? Well, y is going to be 16 times this number. I'll do the exact number, 2 over the 4th root of 5, right? Minus 2 over the 4th root of 5 to the 5th power. So let's see, what do we get? 32 over the 4th root of 5 minus, let's see, 2 to the 5th is 32 over, and then we get 5 times the 4th root of 5. So 1 minus 1/5 is 4/5, so we get 4/5 times 32 over the 4th root of 5, which I think is 64 over 5 times the 4th root of 5. And that's going to be approximately times 64 divided by 5, 19.140. So we'll just say 19.14 units. Except that can't be right. Y can't be bigger than 16. So y is definitely between 0 and 16. So that means I did something wrong. Probably I made an arithmetic mistake here. All right, so let's try that again. That's not y. That's a. I was plugging it into the area function. Okay, so that's an easy fix then. So this, I think this is correct actually. Wait a minute. 4 times 32 is 128. Okay, so it's not right. So the numerator should be 128. Sorry about that. Yep, 4 times 32 is not 64, it's 128. So the 19.14, just double it, and I think it's 38.28. So yeah, let's get rid of this. So this is 38.28 square units, right? So that's the maximum area. But now let's go back and find y. What was y? Y is just 16 minus x to the 4th. Okay, so that should be a little bit easier. 16 minus 16 over 5. So that's 16 times 4/5. Okay, so that's 64 over 5. Which is exactly 12.8. Okay, and that's less than 16, so that makes sense. That makes sense, indeed. Okay, so right, we have x, we have y. Again, here's the exact value for x. Here's the exact value for y. And then the area, well, you could just do x times y at this point, but I did it earlier here. So it's 128 over 5 times the 4th root of 5, or approximately 38.28 square units. And just as a check, if I take 12.28 times 1.34, I get 17.15, which is not right. Okay, hang on. Well, I'll figure this out. That does look like to be about half, but why am I getting half? Okay, so the the fourth root of 5, I should say, is really close to 1.5. It's about 1.5. Okay, so with that, if I take 128 divided by 5 and then divide by 1.5, yeah, I get the 17 again, which is roughly half of what it should be. Let's see, so this is 32 times 4/5. Okay. Yeah, this is just arithmetic error. I was a little closer the first time. This is not 38.28. So just do this one last time. If I take 128 divided by 5, that's 25.6, and then divide by about 1.5, I get the 17. Okay, so yeah, so this is, yeah, so this was wrong here, as I just crossed that out, and this is obviously wrong here too. So this should be about 17, roughly 17.1, and that should be the area. Okay. Yep, and it should be about the same thing. If you do 12.8 times 1.34, that's just x times y times x, you get about 17.1. So, okay. Right, so I'm gonna leave this. This is the exact. This is the exact. This is the exact, right? All right. How do we know it's a maximum and not a minimum? So second derivative test, probably the way to go here, because this is just going to be negative 20x cubed, and it doesn't matter what x you plug in. You're plugging in the 2 over 4th root of 5, 1.34, and it's negative, right? So if it's a negative, it's concave down. Concave down means you have a maximum. In this case, a maximum area. Okay, so we maximized the area of this little rectangle here. And I think that's all we needed to do. So a little bit of arithmetic problem here. I was messing up the numbers, but I think this is correct now. I don't know where I was getting the 38.3 thing, but that was clearly wrong. And yeah, so number 10. Yeah, 17.1 or 17.12 is a little bit closer. So I think that's what the answer key has, and I think that's correct. All right, so moving on. All right, number 11, find the following limits, right? So these are limits to infinity or to negative infinity. And well, let's do part A, which should be easy. So 11a. Right. So 2x squared plus 3x minus 4 all over 5x squared minus 4x plus 1. So how do we find the limit? Well, remember, we take the biggest power in the denominator, that's the squared, and we divide top and bottom by x squared. So I'll just multiply the numerator by 1 over x squared and the denominator by 1 over x squared. And if we do that, what do we get? We get 2x squared over x squared, which is 2, plus 3x over x squared, which is 3 over x, minus 4 over x squared. And in the denominator, we get 5x squared over x squared, so that's just 5, minus 4 over x plus 1 over x squared. Make sense? So notice what happens. Because x is getting bigger, right? This fraction, this fraction, this fraction, and this fraction are all getting smaller, right? These are all approaching 0. Right? Which tells me pretty clearly that when I take the limit, I just get 2 over 5. Or if you prefer, 0.4. Okay. So that was an easy one. But again, you do have to show the algebra here, right? If you're thinking, oh, pre-calculus, right? Remember in pre-calculus, to find the horizontal asymptotes, if they have the same degree on the top and bottom, then you just divide the leading coefficients. So y equals 2 over 5 is your horizontal asymptote. Right, but that wasn't the question. The question was to find the limit, and it'll say algebraically or analytically on the test. So no shortcuts here. You do have to show a little bit of work, right? Not much, but you got to show the algebra here, right? Okay, so part B, very similar. Part C is an interesting one. So let's look at part C. So 11C, we want the limit as x goes to negative infinity of sine x plus cosine x. So there's really not much to show here. You can use the sum rule for limits, right? It's the same as the sum rule for derivatives here. So you can split them up. And what's the limit as x goes to negative infinity of sine of x? Right, there is no limit. The limit does not exist, right? Same is true for cosine. Same is true for tangent, or cotangent, or secant, or cosecant. No trig function has a limit going to infinity or to negative infinity. Okay, so this limit simply does not exist. Okay, right. If you don't know that, well, just look at the graph of the sine function. The sine function looks like this, right? So what happens as you go to the right? You're just bouncing back and forth between -1 and +1. You never get close to any one particular number. You don't get close to 0. You don't get close to 1. You certainly don't get close to 2. But because you're just bouncing back and forth between -1 and 1, right, this is a +1 up here and a -1 down here. Yeah, you never get close to anything. The limit does not exist, right? It's not 0, it's not infinity, it just does not exist. So that's the best you can do for 11C. How about D? So theta goes to infinity of cosine of pi over theta. So let me bring that down here. We're taking the limit as theta. Theta is an angle. Theta goes to positive infinity here. The cosine of pi over theta. Right, so what would that be here? Well, remember, cosine is a continuous function, right? Cosine is a continuous function. That means I can take the cosine of the limit as theta goes to infinity of pi over theta. Now, pi is a constant. That could come outside if you want. You can take the cosine of pi times the limit as theta goes to infinity of 1 over theta. But it doesn't really matter because as theta goes to infinity, 1 over theta goes to 0. So this is just the cosine of pi times 0. Pi times 0 is 0, and the cosine of 0 is 1. So that's the limit. That's the answer. The answer is 1. Okay? I mean, if you think about it, right, what's in the parentheses here? The pi over theta, that's getting smaller and smaller and smaller. It's approaching 0. But what's the cosine of 0? It's 1. So the answer is 1. Okay, so But we can do this interchange of limit here. We can bring the limit inside the cosine because cosine is continuous. Right. Cosine is continuous at 0, at 1, it's continuous at infinity. It's just continuous everywhere. Right. All right, part E. Oh boy, we did one like that, but I guess maybe we should do one more. So for 11e, we want the limit as x goes to negative infinity of 2x plus 1 all over the square root of x squared minus 1. Right. And if you remember, with the square root, it's a little tricky here because the square root of x squared, right, which is the same as absolute value of x, right? It's just x if x is positive, but it's negative x if x is negative, well, not equal to 0, but just strictly less than 0. And because we're going to negative infinity, right, we're going to treat the square root of x squared as negative x, right? Or reverse it, x is negative square root of x squared, right? Again, this is only because x is negative. Okay, so what do? We multiply top and bottom by 1 over x, right? Not 1 over x squared. That would be a little too much here. So we still take the limit as x goes to negative infinity, and we get 2 plus 1 over x all over, and now here's where it gets tricky, right? It's the square root of x squared minus 1 over x. But that's going to be not the square root of x squared, but its opposite. So yep, you need the negative sign here. So I'll just bring the negative sign outside. Right, so we still get 2 plus 1 over x. And now we can take the square root of x squared over x squared minus 1 over x squared, which we can simplify that a little more. Right, so this is going to be the square root of 1 minus 1 over x squared. And now we just use the usual rules of algebra here. This goes to 0, this goes to 0. So we are approaching negative 2 over the square root of 1. So negative 2. Okay? Right, so again, I did take a little bit of a shortcut here. I didn't evaluate the limit of the numerator and the denominator and split them up and so on. But yeah, feel free, right? Once you see x in the denominator, you know that goes to 0, you know that goes to 0. So it's just this part here that does not go to 0. But again, also don't forget the negative, right? This is positive 2, but there's that negative in front. So that's why you get negative 2 and not positive 2. Right. On the other hand, if you're going to positive infinity of the same expression, right, you don't have to do it all over again. Right? You know that you're not going to get the minus sign. So there you would get positive 2. Okay? All right, so that's E. And I guess just to be complete about this, let's do F. So 11F is to find the limit as x goes to, we're back to positive infinity of the sine of x over the cube root of x. Okay. Well, so you remember that sine, right? So first of all, this is not a constant. Unlike the 1 in this problem here, which was a constant, sine is not a constant. So you can't say that this goes to 0 because it's like 1 over infinity, right? Which approaches 0. That's a little sloppy because sine is not equal to 1 unless x is, an odd multiple of pi over 2. Right? But it is bounded between negative 1 and 1, right? That's the range of the sine function. So here's what we can do. And I didn't write it this way here. Right? We can say that this is going to be negative 1 over the cube root of x, which is going to be less than or equal to the limit as x goes to infinity of sine x over the cube root of x. And that's got to be less than or equal to the limit as x goes to infinity of positive 1 over the cube root of x. Okay, so to do this, we also have to use the squeeze theorem. Squeeze theorem from way back in chapter 1. Right? And by using the squeeze theorem, we can say that, well, look, this limit is clearly 0. This goes to 0. This goes to 0. So what's between 0 and 0? 0, right? So by the squeeze theorem, and you should mention that, or at least write out the three equations here, right? Or the two equations. But either way, by the squeeze theorem, we can say that the limit as x goes to infinity of sine of x over the cube root of x has to be 0. Okay, so the answer here is 0. But by the squeeze theorem or by splitting it up into the three separate parts here. Make sense? All right, so that's 11. Okay, so for number 12, this is the more recent stuff, right? This is in 4.1. Okay. So make sure you know the rules for antiderivatives, and that should help. So let's just start with part A. You have 18 x to the 8, it's supposed to be an 8, minus 1 over x cubed, well, that's just x to the negative 3, plus pi times 1 over cosine squared is also secant squared. So by the sum rule and constant times function rule, I think we can split this up here. Take out the pi. And yep, so this is just going to be 18 times, let's see, 1 over 9 x to the 9 minus, let's see, this will be negative 2, so 1 over negative 2 x to the negative 2 plus pi times the integral of secant squared is tangent. And then don't forget your c, your constant of integration. So to simplify this, I guess we get 2x to the 9 plus 1 over 2x squared plus pi times tangent of x plus c. Again, the c is also very important. If you don't put the c, you're going to lose a point for that. Okay, so part A, I think pretty straightforward. Nothing tricky about that. What about part B here? I'm wondering if I can squeeze that in here. Oh, let's do it up here. So the integral of x squared minus 3 times the square root of x all over the cube root of x dx. Well, it's a quotient, right? But there's no quotient rule for integrals. So luckily, the denominator is just a single term, right? It's a monomial. So we can split this up. This will be this, the integral of x squared divided by the cube root of x, right? Minus 3 times the square root of x divided by the cube root of x. Okay, and now, let's see, 2 minus 1/3 is going to be 1 2/3, so 5 over 3, I think. Minus 3 times 1/2 minus 1/3 is 1 over 6. And now by the same rules as we did over here on the left, 5 over 3 plus 1 is 8 over 3, so we get 3 over 8 times x to the 8/3. And then 1 over 6 plus 1 is 7 over 6. So minus 3 times 6 over 7 is minus 18 over 7 times x to the 7 over 6. And again, don't forget your plus c. And personally, I would leave it like that. I would not bother writing it with radicals. This way is just as easy. So that was part B. Part C, I do that down here. So we had the integral of 2x minus 1 times x squared minus x plus 4. If you were taking the derivative, I would probably just use the product rule. But there is no product rule for antiderivatives. So in this case, we don't have a choice, right? We have to multiply it all out. So this is going to be 2x cubed minus 2x squared plus 8x. And then distribute the negative 1, and we get negative x squared plus x minus 4. So 2x cubed minus 3x squared plus, 8x plus x is 9x, and then minus 4, all with respect to x. And I'm not going to bother splitting it up. I think we can all do this in our heads, right? 2 over 4 is 1/2 x to the 4 minus x cubed, right? 3 over 3 is 1. And then plus 9 over 2, x to the 2, minus 4x plus c. And that's good enough. So that's part C. Part D is a little bit tricky, so let's take that a little bit slower. We do the integral of sine of theta divided by 1 minus sine squared of theta, d theta. Right, so again, just like in part A, there's no quotient, or part B rather, there's no quotient rule, right? So we can't split that up in any ways, right? And we can't split up the denominator because it's not a single term, it's a double term, it's a binomial. So it's not like we can simplify it like we did part B. Okay, so what can we do? Well, we can simplify it if you know the Pythagorean identity, right? Sine squared plus cosine squared is 1. So the denominator here, 1 minus sine squared, is cosine squared. Right? That's really the only way I know how to do this, right? And now, how does that help? Because there's still no quotient rule. Well, this is going to be 1 over the cosine times sine over cosine. But there's no product rule. On the other hand, 1 over cosine is just secant of theta, and sine over cosine is tangent of theta. Now this should look familiar, right? This is one that you have to know by heart. The integral of secant tangent is secant plus c. Right? The derivative of secant is secant tangent, so the integral of secant tangent is secant. If you prefer, you can write it as 1 over the cosine, but I don't see why. I mean, I'll accept either, of course, but it's just secant of theta, which is the same as 1 over the cosine. Okay? Right, not arc cosine, right? Not, yeah, please don't write it as cosine to the negative 1, because that's arc cosine, not the same thing. And in fact, theta is not an angle, it's a number here, right? You know, if you insist on writing it with an exponent, at least put the negative 1 on the outside so that we know that this is not the same as inverse cosine. But yeah, that's still an awkward way to write it. I would either write it this way or this way, not that way. Right. And certainly not arc cosine. So make sure you know the difference. Okay, part E, very quickly here. We have the integral of v squared plus 4, cubed. Right. So if you were taking the derivative, you could make a case for using the chain rule. But because there's no chain rule, we don't have a choice. We have to multiply it out. So what do we get? We get v to the 6 plus, let's see, 3v to the 4th times 4, so 12v to the 4th times, yeah, 12v to the 4th, I think that's right, plus 16 times 3, 16 times 3 is 48, v squared, plus 4 to the 3rd, 64. So binomial theorem comes in handy. If you have to multiply it out term by term, that's okay. It just takes a little bit longer. Now we just use the sum rule, right? There's, of course, a sum rule for antiderivatives. So 12 over 5, v to the 5th, plus 48 over 3, I think is 16. Sorry, it's not an x, it's a v. Plus 64 times v plus c. And feel free to leave it like that. I think that's good enough. And finally, part f. That should be the easy one here. The integral of 2 times the 7th root of t to the 4th dt. So take out the 2 and rewrite this as t to the 4 over 7 and just use the power rule. Right? So the power rule, remember we add 1. 4 over 7 plus 7 over 7 is going to be 11 over 7. And then divide by 11 over 7, or multiply by 7 over 11. So I think we get 14 over 11 times t to the 11 over 7 plus c. Right. Or if you insist on writing it with a radical, then you still get the 14 over 11. But then in the numerator, what do we get? We get t times 11 minus 7 is 4, right? So 4 over 7, so the 7th root of t to the 4. Oh, plus c. Don't forget the plus c here. So either way is fine. And that's it for integrals. Again, some will be tricky, like the sine one. Others, you just have to make sure you don't do silly things like use an imaginary product rule or an imaginary chain rule, because there aren't any for integrals. There are techniques that mimic the chain rule and the product rule, but we don't call them product rule and chain rule for a good reason. Right? So we will get to sort of the reverse chain rule here, but in fact it doesn't even apply in this case. So even with the techniques, this way is pretty hopeless without having to multiply it all out. So in some cases, those techniques are simply not going to work here, right? So yeah, at least for this test, all you need is the sum rule and the constant times function rule and the power rule, of course, and being able to split them up. And all the trig functions, right? After all, you should know the integral of secant times tangent is just secant plus c. Okay, moving on. Okay, moving on. Number 13, we have the acceleration of a particle moving along the x-axis. So, we called it s here, but I would just call it x. So the acceleration, and remember the acceleration is the second derivative of the position, which is also the first derivative of the velocity, is equal to 12 times t plus 4. And this is in meters per second squared. Okay. So how do we find the velocity? Well, we have to integrate the acceleration. Right. Don't take the derivative of the acceleration. That would be the third derivative of the position, or the second derivative of velocity. Right? We want to go backwards, right? So we want to integrate 12t plus 4 dt. And I hope you can do that in your heads, right? That's just going to be 6t squared plus 4 times t. Don't forget your constant c here. Right? So, yeah, with that constant, this formula looks kind of pointless. So if I plug in, t equals 2, for example, you're just going to get some number plus any number. So it's going to be arbitrary. So that's not going to help, right? So notice what else we're given here, that initially it was moving 14 meters per second. So this is our initial condition. The velocity, the initial velocity was 14, right? 14 meters per second. So now if we plug in 0 for t, that's our initial velocity, we just get 0 plus c, which is c, and that has to be 14. Right? So, yep, it turns out that c is just 14. So plugging that in to the velocity function, we get our velocity function, and that's part A. Okay, oh, I'm running out of space here. But I think we can squeeze in part B rather. The position function, we just have to integrate the velocity. That's a plus, right? And that's pretty easy, right? 6 divided by 3 is 2, so 2t cubed plus 2t squared plus 14t plus another c. And I don't want to use the same c, so I'll call it d. But we know that the initial position, oh, I got to go up here, the initial position was negative 2. Right? So it was initially at this position. So s of 0 is negative 2. And so when you plug in t equals 0, right, you just get 0 plus d, which is negative 2. So d is negative 2, and that tells me that my position function in terms of t is this. Right, and that's it. Right, so finding the velocity from the acceleration is just taking one integral, and then finding the position is taking another integral. So you just do one and then the other. And that's it for number 13. All right, and one last problem on the practice test is number 14. And we have the rate of, oops, sorry, I'm cutting off the p here. So the rate of growth, the derivative of the population, dp over dt, is proportional to the square root of t. P is the population of the number of bacteria, right? And t is the time in days. And t is between 0 and 10 in this problem here. So in other words, this formula will only be valid between 0 and 10 days. After 10 days, we might have to find a different model. Okay, so it turns out this just means, and they give us the equation here, that the derivative of p is equal to some constant k times the square root of t. And the initial population, so the population at time t equals 0, was 500. And after 1 day, the population after 1 day, it was 600. Okay, so we know that. We want to estimate the population after 7 days. And again, 7 is less than 10. So, yep, how many bacteria were there after 7 days? That's the question. Okay, well, so if we know the rate of change of the population, how do we find the population? We know the derivative, right? And it's just equal to k times, well, how about t to the 1/2? Right? So now to find p as a function of t, we just have to do the opposite. Take the antiderivative of k times t to the 1/2. So that k is a constant, that can come outside. And then t to the 1/2, well, that's a power rule, right? So that's going to be 2/3 times t to the 3/2 plus c. Yep, be careful you don't do 1/2 t to the negative 1/2. That's the derivative, not the antiderivative, right? So now we have our formula for p as a function of time. It's going to be 2k over 3 times t to the 3 over 2. And then don't forget the plus c here. Okay. So you notice the issue here. We can't just plug in 7 yet because we'll get some number times k plus c. And if we don't know what k is and we don't know what c is, then that's useless, right? So before we plug in the 7, we might want to plug in 0 first. If we plug in 0, we just get, well, 2 over 3 times k times 0 is just 0, and 0 plus c is equal to 500. Right? So yeah, that tells us that c has to be 500, which means p is now, you know what? I'm going to do it down here. P of t is still 2k over 3 times t to the 3 halves plus 500. But we still can't plug in 7 because we're going to get some number times k plus 500. And if you don't know what k is, then we don't know the population. Okay, so what else do we know? We know the population after 1 day. P of 1 is 600. So at this point, maybe we should plug in t equals 1. So we get 2k over 3, right, times 1 to the 3 halves plus 500. And that equals, I forgot, 600, right? 600. Right. This is a 5 here. Okay, so I think we can solve for k. We get 2k over 3 times 1 is equal to 600 minus 500, which is 100. So k is going to be, k is going to equal 300 over 2, which is 150. Okay, so now I think we have a formula for p, right? 2k over 3, so 2 times 150 is 300. 300 divided by 3 is 100, times t to the 3 halves plus 500. So there's our formula for p. And now we can plug in any t. Well, not any t between 0 and 10. But 7 is between 0 and 10. So now what happens when t is 7? We get 100 times 7 to the 3 halves plus 500. So 7 to the 3 halves is 7 times the square root of 7. So we get 700 times the square root of 7 plus 500. Right? And that's the exact answer. But right, we're modeling number of bacteria. So what is this approximately? Again, just shove it into your calculator. What's the square root of 7? It's about 2.645, so multiply that times 700, and then add 500, and I get let's try that again. We get 2,352.0259, but we're not going to count fractions of a bacteria. This is the number of bacteria after 7 days. So it's about 2,550, say that again, 2,352 bacteria. Right. Starting with 500, then 600, so you can tell the number of bacteria is increasing, but not exponentially, right? So you have to be careful here. If you're using the, P0 e to the kt, you're using the wrong function here. We will talk about exponential functions when we get to chapter 5, but we're not there yet, right? We're not there yet, and so, you have to use this formula for the population of, or the rate of growth of the population, right? And then this is the formula here. Yep, this one here in purple. This is not an exponential function, right? So it is a power function, but it's not an exponential. In other words, the exponential function might look like this. The graph of this function here might look like this. So it doesn't increase quite as rapidly as an exponential function. Okay, so I hope that helps. Again, finding the antiderivative. If you know the derivative and you want the original function, you have to take an integral or an antiderivative. Right? And the rest of the problem is figuring out what k and c are. And again, we needed 2 initial conditions, not just 1, right? Because there's 2 constants, right? There's the k and there's the c. So if you just know 1 initial condition, that might allow you to find c, but then you don't know what k is. So we needed both of these conditions to find both k and c. So I hope that helps. And there you go. That's the practice test 3. So that's my review for test 3. Best of luck.